These ships are the means of transportation of millions of people and goods of every kind between countries, and are therefore the lifeblood of trade between nations. This ship is one of the many engaged in this vital task, and the functioning of all its parts in unison is essential if its role is to be played efficiently. As with people, no two ships are exactly alike. Although ships of the same class may be built to the same exacting specifications, they will not all meet the same conditions in use, and they will therefore acquire certain characteristics which will be particular to them. The power source is no exception to this, and depending upon the conditions it meets and the attention it receives, it will function either as it was designed to or below that standard. One of the main factors in the correct functioning of the marine diesel engine is the quality and condition of the lubricating oil in the system. Correct treatment of engine crankcase oil helps to reduce wear of the engine parts. The life of an oil can be several years, but will yours last that long? Failure of adequate quantity and quality of lube oil can cause damage. To ensure this does not happen, we need to know the types of problems causing degradation of the oil, the steps necessary for prevention and treatment of contamination, and analysis of the oil's condition. When the oil is delivered to the ship, it will be in an on-spec condition. This is the standard to which the oil company has carefully produced the oil in order to meet the needs of a particular engine. Care needs to be taken with the oil in storage and handling. Even a little contamination will impair the quality of an oil and will in time take its toll in excessive engine wear. Following correct procedures will ensure that the oil is maintained in good condition. Good housekeeping aboard ship is the key to efficient and effective lubrication. Ensure that you order enough for your needs. Check records of earlier voyages as a guide to consumption. Before delivery of the oil, the storage tanks should be inspected to make sure they're free of loose paint and rust. Before loading begins, the filling line should be drained at the lowest point. If filling lines are used for more than one grade, they should be drained thoroughly and shutoffs should be checked for leaks. Tanks are subject to water contamination due to leakages around filling points, tank breathing, and incorrect venting at points of high humidity in the engine room. Having ensured that the oil is in the best condition possible before use, let us look at the engine oil system itself. The oil in the system of a diesel engine serves both as a lubricant and coolant, carrying away heat from the bearings and other components. Many oils have a range of additives which help to combat contamination. During normal operations, the crankcase oils become contaminated by carbon, metal, water, and dirt. The following problems are caused: excessive wear of cylinders, rings, and pistons, excessive deposits on pistons, valves, cylinders, and ports, crankcase corrosion, and bearing failures. The exact nature of the problem depends largely on the type of engine. Let us look first at the crosshead type of engine. All the working parts of a crosshead diesel engine, other than the pistons and cylinders, are served by the bearing oil circulation system. In a typical system, the lubricating oil circulating pump takes suction from a drain tank, sometimes through a gauze strainer, and delivers oil through an oil cooler and a filter to a gallery pipe. From here, the oil is distributed to various engine bearings, including the thrust block, and if applicable, to the piston cooling system. Taking a sump reading at regular intervals is most important. A rise in the sump level indicates that external liquids are entering, and a drop in the level shows oil is being lost. The first step in the removal of contaminants is static filtration. These filters are made out of a variety of materials, such as wire compressed paper, pleated fibre paper, mesh felt, and plastic, and can be self-cleaning and self-flushing. Filters may get choked, and care must be taken to ensure there is no reduction in the oil flow to the engine. Engines have been starved due to blockages at filters. Very fine filtration can be attained. Attention should be paid to the manufacturer's recommended running hours, and one's own experience of particular engines must be taken into account. Strainers are used to take out large debris, rust and scale in full flow treatment. The coarse filters are fitted on the pump suctions. The fine filters of 0.02 to 0.04 millimeters are fitted on the discharge to the engine. These are used in bypass, as the volume of oil circulated is too great to enable these to be used in full flow treatment. Duplex or two-element type filters are used, so that one may be cleaned while the other is in service. A dual density element enables the combination of partial flow and full flow treatment in one filter element. Differential pressure gauges connected across the filters indicate when cleaning or removal of the element is required. Some small filters are self-venting, but in the large discharge types, air can collect, and these are vented and piped to the engine crankcase or lubricating oil drain tank. Magnetic filters are sometimes used in bearing oil systems. The oil passes through filtering cages, and the ferrous metal is trapped by powerful magnets. Frequent inspection will show up any abnormal wear of magnetic engine parts. Some filters combine a clarifying element with a coalescer, which removes all free water from the system. The dirty oil is forced through an inorganic fibre element, and the minute water droplets are coalesced into large droplets, which settle out by gravity to the bottom of the filter. Ensure you know what type of filters you have, how they operate, and how they are to be maintained. Refer to the manufacturer's manuals on board. Let's now look at the purification by centrifuging. This is the most widely used method for purifying diesel engine lubricating oils. The lube oil in the diesel engine sump tank is pumped via a preheater to the centrifugal separator and discharged back to the sump tank. The oil is normally heated to about 80 degrees centigrade. Overheating will cause oxidizing of the oil. The capacity of the centrifuge doesn't allow full flow treatment of the oil. This model of a separator shows the main components: a frame, a worm gear, a spindle, a bowl, and inlet and outlet ports. The separator bowl consists of a bowl body and a hood held together by a lock ring, a distributor, top disc, wing insert disc, and a disc stack which consists of conical discs. The disc thicknesses are about 0.5 millimeters, and the separation channels, the distance between the discs, is about 0.6 millimeters. Separation takes place between these discs. The space between the periphery of the bowl body and the disc stack acts as the sludge space for the particles separated from the oil. In the purification process, the dirty oil is introduced into the bowl through the inlet. The oil is accelerated in the distributor to higher and higher rotational velocity, so that when the oil is introduced into the bowl at the periphery of the disc stack, it has almost the same velocity as the bowl itself. The water and solid particles are separated from the oil in the disc stack. The water flows continually through the channel formed by the bowl hood and the top disc, passes the gravity disc into an outlet chamber, from where it is discharged by means of a so-called pairing disc. The particles are collected in the sludge space. The purified oil is discharged through the oil outlet by means of a similar pairing disc located in the oil outlet chamber. The fluid velocity in the bowl increases as the distance from the center towards the periphery of the bowl increases. Thus, to prevent the occurrence of slips between water and oil at the interface, a special insert disc with wings is placed in the middle of the disc stack. The wings keep the water and oil rotating at the same angular velocity. This arrangement ensures the highest possible separation efficiency and also reduces the risk of emulsification between oil and water at the interface. Separation takes place in the disc stack, so its full area should be utilized. This is achieved by locating the interface, which is the division of oil and contaminants, between the outer edges of the disc stack and the top disc. Should the interface be located outside the edge of the top disc, the oil will escape through the water outlet. To prevent this, the bowl is filled to the edge of the interface with sealing water. The sealing water is forced against the periphery of the bowl, forming a liquid ring, the inner side of which acts as a liquid seal for the oil. The inner diameter of the gravity disc fitted onto the water outlet determines the location of the interface. The separator can work either as a purifier or a clarifier. In the purifier, the water separating out to the sludge space is continuously discharged via the space between the top disc and the bowl hood. As a clarifier, this water outlet is closed and water separated out is collected in the sludge space. Purification is recommended for marine lube oils due to the risk of water contamination. There are two basic types of separator: manually cleaned and self-cleaning. Manual cleaning is by a solid wall bowl. The separator is intermittently operated, and when the sludge space is filled, the machine is stopped and emptied. In the self-cleaning separator, the sludge ports in the bowl hood are revealed by a hydraulically operated sliding bowl bottom. Self-cleaning separators can be arranged for total or partial discharge. Most modern ships have partial discharge for economic reasons, less oil waste. Now let us look at separator performance and the points to watch to get good separation results. As stated, the interface between oil and water must be correctly positioned outside the disc stack in order to clean the oil satisfactorily. The interface will move from its correct position into the disc, resulting in bad separation if there is a decrease in density, viscosity, or flow rate, or an increase in temperature. The interface will again move from its correct position towards the periphery of the bowl, ultimately resulting in a broken water seal if there is an increase in density, viscosity, or flow rate, or a decrease in temperature. A change in pressure drop over the disc stack will occur due to changes in flow rate, density, viscosity, or temperature. In order to get the interface in the correct position for a good purification result, the following are important. First, the correct gravity disc must be fitted to suit the prevailing density, viscosity, and flow rate, and is chosen in accordance with the maker's instruction manual. A general rule of thumb is that the gravity disc having the biggest possible inner diameter that does not cause a broken water seal is the correct one. Secondly, the separator should be operated at the optimum throughput and at a constant separation temperature. And thirdly, the sludge space must not be overloaded, as then part of the disc stack may become blocked with a following reduction in separating area. Local conditions must determine the most suitable running times between sludge removals, but experience has shown that anything between 1 and 4 hours gives satisfactory results. Separators are rated for purifying diesel fuel oil. When treating straight-type lube oils, the separator should be operating at 35 to 45% of the nominal rated throughput. When treating detergent-type oils, the corresponding throughput is 20 to 25% of the rated throughput. The throughput should be adjusted to ensure minimum contamination in the total oil system. If run at a lower throughput than optimum, the oil leaving the centrifuge will be cleaner, but sludge content of the whole system will be higher due to the smaller amount of oil treatment per hour. If higher than optimum, there will be a greater volume of treated oil, but it will be less clean, and so again, sludge content of the whole system will be higher. It is recommended that the separator be operating at all times that the engine is running. When in port and the engine stopped, it is advantageous that the oil be passed through the separator at the slowest possible speed to take out smaller particles of contamination. When opportunity allows, the complete oil charge should be pumped to a renovating tank, where it is heated and settled over 24 hours. After draining off the impurities, all the oil should be run back to the engine via the centrifuge as slowly as possible. The separator is subject to wear and tear and should be maintained and operated correctly to keep it functioning efficiently. It is installed to protect the engine, and if it does not function as designed, the final result will be bad separation, which will cause more wear and tear of the engine. In conjunction with static filtration and centrifuging, a routine analysis needs to be undertaken. This will monitor the condition of the oil, any changes in quality, and the effectiveness of the treatment applied. Analysis is a service provided by the oil companies. For a more immediate indication of the oil condition, test kits can be used on board. Simple tests can give a useful analysis in a short time to check the alkalinity, dispersancy, contamination, viscosity, water content, total acid number, and total base number. Tests for water content should be carried out daily on board. As the result coming from the sample reflects the state of the whole oil, two essentials should be observed. These are that the sample is not contaminated during or after drawing, and that it is representative of the whole oil charge. Failure to observe these 2 points will result in misleading information. In large engines, oil should have been in circulation for some time before the sample is taken, and about 5 litres of oil should be drawn off before filling the sample container. The oil should be hot when the sample is taken, and come from points before and after the centrifuge. A full shore laboratory analysis should be carried out every 3 to 6 months, unless there is suspected degradation. The figures obtained from such analysis when received on board should be checked with existing figures. In the case of an oil which is badly contaminated and is condemned, the sump must be opened up, examined, and cleaned prior to replenishing with new oil. In normal circumstances, the sump should be examined once a year. We now look at the trunk piston engine, in which the pistons, as well as the bearings, are lubricated by the crankcase oil. Oil under pressure is fed to the main bearings and thence by way of drilled holes in the crankshaft to the big end bearings. From these, the oil is usually led by drillings in the connecting rods to the small end bearings. Then it goes to the piston cooling system. Piston ring and cylinder lubrication is by splash from the crankcase. In some medium-speed trunk piston engines, lubrication of the pistons and cylinders is supplemented by means of separate cylinder lubrication. Detergent oil is normally used in the systems of trunk piston engines. In the larger types, the oil is filtered and centrifuged in the same manner as for the crosshead type of engine. In the past, the oil in smaller engines was filtered, but not usually centrifuged. But due to the introduction of heavy fuel, the oil must now be both filtered and centrifuged. The system charge is comparatively small and is renewed periodically as recommended by the engine manufacturer, or more frequently if found necessary due to abnormal contamination. Fuel dilution, the contamination of the lube oil by fuel leaking in the engine, is always a danger in trunk piston engines. The fuel injectors must be given proper attention to avoid leakage into the crankcase. If the oil flow through the engine is too low, the additives will be more rapidly depleted. Piston temperatures, oil consumption, and additive level are closely related factors. An apparent improvement or economy in one direction only could have a bad effect on the operation of the engine as a whole. Samples of lubricating oil are taken regularly. For diesel engines, the samples are taken from the system of a low-speed engine and from the crankcase of a trunk piston engine. These samples are returned to the oil supplier for analysis. The sample should be forwarded in a suitable clean container and not in various glass bottles. Clear labelling, giving details of the source of the sample, the type of oil and total hours in use, should accompany the sample. Analysis of samples indicates the condition of the oil and whether it is fit for further service. The results should be assessed in relation to past analysis. The rate of change in quality is important. In analysis, the first question is obviously, is the oil usable or not? The second is, will the machinery continue to operate satisfactorily with this oil? Several factors and possible contamination sources are considered. Take the change in viscosity, for example. It can be lowered by fuel dilution and raised by oxidation, contamination by cylinder sludge and heptane insolubles, that is, products of combustion or soot. Changes in viscosity have to be considered in relation to other test data, such as the total acid number, TAN, for oxidation, H-heptane, and water for contamination, closed flash point for dilution by light fuel and cleaning fluids. Change in viscosity index could even be due to mixing with other oils. Some other factors to consider. Water content, which can be from a leaking cooler, leaking liners, or condensation. Salt from seawater leakages can cause corrosion. Insolubles, sediment from oxidation, combustion, soot, wear debris, dust and grit from system pipelines, flash point, lowered by fuel contamination, total base number, TBN, alkalinity depletion by acids from combustion products and oxidation, microbiological degradation. Tests for these can define the condition of the oil and point to the action which needs to be taken. This may mean changing the oil or treating it in a particular way by settling and centrifuging. When one considers the many tons of oil that may be in use in one engine oil system, it is clear that oil hygiene can lead to economic benefits and smoother running of the engine room. Wear of machinery will be greatly reduced, and there will be even more efficient engine operation. A diesel engine which is used and not abused will give many years of satisfactory service. Crankcase oil hygiene will contribute to the safe and efficient operation of your vessel.